Mirrors are glass polished from one side to reflect nearly every type of light. Those mirrors could be flat or even curved mirror, which means it's part of a sphere. Whatever was the type of the mirror, it caused the light to reflect or bounce off. When we have a regular surface, such as mirror, or even a surface of water, or we can say a specular surface, which means a shiny surface. That mirror with a smooth surface produces regular reflection. If we have a regular surface and perpendicular to that surface we have the normal, and by convention all angles in geometrical optics are measured with respect to the normal. And as we said, normal is the line perpendicular to the surface, whatever was that surface, lens, prism, or the mirror. So when we have that regular surface or specular surface, such as mirror or water surface, the incident ray here will reflect at angle equal to the angle of incidence. So I, the angle of incidence, equal to R, angle of reflection. And because the surface is regular, all incident ray will fall and reflect at the same angle, with same angle. So this one here will equal this one here, will equal any incident ray on that specular surface. This will give us a clear and shiny image. If that surface was irregular, or we can say rough surface, such as white paper, this surface also we call it irregular. Unlike mirrors, most natural surfaces are rough, cause the light reflections in many different directions, irregularly or diffusely. So the irregular one, we also can call it the diffuse reflection. This one, regular or specular reflection, but with rough surface we call it irregular or diffuse reflection. In this rough surface we have normal like that. This one perpendicular to the surface. This is the normal for this area. This is the normal for this area, since as we said normal is perpendicular to the surface. As you can see, each point has different direction of normal, but all are perpendicular to the surface. So the incident ray here will be like that, reflected this way. This one will be like that and reflect this way. The same for this one, will reflect this way. So the reflection is irregular. The angles here are different. So the diffuse reflection will help to see the objects, but they are not shiny. So the light irregular reflection, all the rays will reflect in same direction, but in irregular reflection, the light will reflect in different directions. Whatever was the type of reflection, we have law that state always the angle of incidence equals the angle of reflection. So I all the time equal R. And here we have the normal, incident ray, and reflected ray, all at the same plane. Back to our polished glass or the mirror. If we have plain mirror, which means a flat mirror, and you take a look at your face, this is your right side and this is your left side. Let's put watch here perhaps so you can differentiate between the directions. The plain mirror always form virtual image. And virtual image, we cannot put it on screen. Virtual image also always erect. So here you are, erect, not inverted. And also have the same size as the object, the same width, the same height. All the dimensions are similar to the object. The distance between the object and mirror is the same as the distance of the image and the mirror. So if you are 5 meters away from that mirror, the image here will appear as 5 meters away from the mirror. Most important characteristic of the image that formed by plain mirror, the image here is reversed, or also we can say laterally inverted. What's that supposed to mean? Inverted means upside down, but laterally inverted or reversed means the right side of the object become the left side in the image. So the watch here will become at the right of the image, reversed or laterally inverted. This is for the plain mirrors, that's the first type of mirror, and we have another shapes of the mirrors such as spherical mirrors, which means they are part of sphere. They are curved mirrors. So we have a hollow sphere, which means it's empty from inside. And we cut our mirror from any part of that sphere. Here it is, our spherical mirror. If we painted that mirror from inside and the light will reflect from outside, that's a convex. If the opposite, we polished or painted that mirror from outside and the light reflected from inside, that's immediately the concave. Easily or simply we can draw the mirror like that. That's the glass and that's the polished direction. Let's do the same for the concave. It will be like this. That's the glass and this is the polished direction. Here we have the convex, the glass with the polished direction. Here in mirrors also we have the focus point for both the concave and convex mirror. Concave mirror give real inverted image if the object is beyond the focus. If it's at point farther than the focus of that mirror, the image will be real and inverted, like this. But if the object has a distance less than the focus, which means at some point here, then we will have a virtual image. And it will be erect, enlarged image. As for convex mirror, it always gives a virtual image. Erect and also diminished one. And that image always forms behind the mirror, which means immediately the opposite side of the object. So, as you can see here, it's quite opposite the lens. Here in concave mirror, we have the same characteristics of convex lens. We can have real inverted image or we can have virtual erect image. The difference here, lens, when we have a real image, it will be at the opposite side of the object. But in mirror, when we have a real image, it will be at the same side of the object. Quite the opposite in convex mirror, similar to the concave lens. But here in virtual image, the image will be at the opposite side of the object, while in lens, the virtual image will be at the same side of object. This is the concave lens. The virtual image will be always at the same side of the object. This is our concave mirror painted from outside. So this is the hard surface. And this is the reflective surface. This is our optical center. When we have incident light coming, they will reflect back from the concave mirror to collect at point we call it the focus point. The concave mirror here will converge the light. So the concave mirror also is a positive mirror and converging mirror. Any object placed very close to the mirror at distance less than the focus, the image will be virtual and magnified. When we put the object farther from the mirror, the formed image will become real and the size of that image will reduce. So this concave or converged mirror can form a small or large image, and it could be real or virtual image. The sphere that we cut our mirror from it has a center. The center of this sphere equal 2 times the focus point, which means the center of the mirror equal to focal length, the distance between the mirror and F, the focus point, is the focal length. In the convex, this is the axis and the hard surface from the inside. The convex mirror will diverge the light, which means we will have the focal point at the opposite direction of the light. So our convex mirror is negative and it diverges the light. In concave mirror, if we place our object at infinity, we will have a real image, and since it's real, it will be inverted. This image will form at the focus of the mirror, and the size will be very small compared to the object, so it will be diminished. As you can see here, the angle of incidence always equal to the angle of reflection. If this one 30, this one will be 30 also. The distance between the center and the mirror equal to focal length. If we place that object behind the center of curvature of that sphere, we will have a real inverted image between the center and the focus, and the size will be smaller than the object. If we place the object at the center of curvature, the image will form also at the center of curvature. And of course, it will be real and inverted. The size of the image now at the same as the object side. If the object placed between the center and the focus, the real image will form behind the center of curvature. And of course, it's inverted. The size now is larger than the object. So when we go closer to the mirror, the size of the image will increase. This image will form behind the center of curvature. When we place the object at the focus, the real image will form at infinity, and it will be real, inverted, much larger than the object. All of the formed image by the concave mirror is real unless we put that object between the focus and the mirror. In this case, we will have a virtual erect image. But in mirror, the virtual image will form at the opposite side of the object. This is our object. The opposite side we will find our image. If the image is real, it will be at the same side of the object. So quite the opposite of the lens. In this case, when we put our object between the mirror and the focus, our virtual image will be larger than the object. Those for concave mirror or the converging mirror. What about the convex mirror or the diverging negative mirror? The image formed by convex always virtual. Wherever we put that object, the image will be virtual and erect. If we place the object at infinity, the virtual image is formed at the focus. And of course, since it's virtual, it will be on the opposite side of the object. The size of the image is much smaller than the object. When we put that object at distance less than infinity, which means we can put it at finity area, some point near the convex mirror, we also will have a virtual image, but this time it's between the mirror and the focus. The size of the image is smaller than the object. This is our convex mirror, and this is the concave mirror. In the middle, we have the optical axis or the principal axis. And this is the focus point for both. And this is the center of the sphere that we cut the mirror from. Any ray come parallel to the optical axis will pass through the focus after reflection in concave mirror. In convex, the parallel ray, after reflection, it seems like it's coming from the focus. And if that ray came passing through the focus, it will reflect parallel to the optical axis. After reflection, in convex mirror, it appears that ray passing through focus like that, it will reflect parallel to the optical axis. If that ray passes through the center of the curvature like this, after reflection, it will follow the same path via the center of curvature again. In convex mirror, the ray that appears to pass through the center of curvature, after reflection, it will come back via the same path again. Here in this point where the mirror meets the optical axis for convex and concave mirror, we call it pole. When ray incident at pole is reflected back, the angle of incidence here equal the angle of reflection for both convex and concave mirror. As you can see here, this is the path of the light. Normally, the light should complete its path in the same direction, but the mirror inverted back, which means the direction of light now, because of reflection, will go in the opposite direction. For that, when we want to find the power of mirror, we can use the same lens formula, which states the power of the lens equal 1 over the focal length of that lens. This one for lens, since the light keep going in the same direction. But in mirror, since the light will return back again, and that's something abnormal, we need to put the negative sign in our formula. So the power of the mirror equal 1 over focal length, but we have to put the negative sign. So this one will be for the mirror. And we also here measure it by diopter. If you notice, the center of curvature for this mirror to the focus point have the same distance between the focus point and the pole, which means this one equal this one. So the radius of curvature for the mirror equal to focal length. That immediately means the focal length equal half radius of curvature. So if I have the radius of curvature, I can also use it to find the power of the mirror. So the power of the mirror also equal minus 2 divided by the radius of curvature minus sine, as we said, because the mirror changed the direction of the light to the opposite side. But be careful, this one for the mirror, not for the lens, because not all of the time and not all of the lenses, the radius of curvature equals to double focal length. So this one, we use it in mirror only. But the same way of sign conventions for lenses, we have the same sign conventions for the mirror. This is the mirror, and this is the optical axis or the principal axis. This is the convex, and this is the concave. Since the concave collects the light at the focus, that means the concave mirror is convergent mirror, which means it has positive power. While the opposite in convex, it seems to collect the light at the focus. So we have to imaginary complete the light to since it's coming from the focus. The convex mirror diverge the light. So it has negative power. This is the mirror. Anything to the left of mirror is negative for both convex and concave, and anything to the right side of the mirror will be positive. So the same way of lenses. So if we have an object in front of the mirror, the distance between the mirror and the object will be negative, since the object always to the left side of the mirror, or we say in front of the mirror. The forming image in mirror, if it's real, it will be at the same side of the object, which means to the left. So the distance between the mirror and the image will be also negative, since it's to the left. If that image was to the right, which means virtual image, the distance this time between the mirror and the image will be positive. The second thing, anything above the axis will be positive. Anything beneath the axis will be negative. So for example, the height of the object here is positive since it's above the optical axis, and the height of the image here is negative since it's beneath the axis. What about the focal length? Concave mirror, which has positive power, its focal length always negative. Quite the opposite. Convex mirror, which has negative power, its focal length, since it's to the right, always positive. That's a little bit confusing, but you have to take care of those sign convention. And also here, in mirrors, we have the divergence power. Divergence power when we depend on the triangle that made by the light. So if we have the object here, the distance between the mirror and the object can give us the power of the divergence here. So the divergence of incidence here equal 1 over the distance between the mirror and the object. And when we form image here, we can depend on the distance between the mirror to give us the divergence here. So the emergence divergence equal 1 over the distance between the mirror and the image. And of course, divergence is power, so we measure it by diopters. The divergence of this one, the emergence one, will depend on the incidence divergence and the power of the mirror. So we can say the divergence of emergence equal the divergence of incidence plus the power of the mirror. So as you can see, the same formula that we use in lenses. And of course, don't forget the sign of conventions. From here, we can say 1 over the distance between the image and the mirror plus the distance between the mirror and the object will give us 1 over the focal length. Shall we put the negative here? No. The negative sign just on those power formula of the mirror. That's all. Here you can only use the normal sign conventions. Since we always put the object in front of the mirror, which means to the left side, that means it's always negative here. And from those, we can find the magnification formula by the mirror. The same way, in magnification, we can depend on the height of the image divided by the height of the object to give us the magnification. So if the height of the image was 12 centimeter and the height of the object was 4 centimeter, the ratio between them will give us the magnification. 12 divided by 4, this one will give us the result 3, which means the magnification occurs by this mirror is 3 times the object. We also can depend on the distance between the object to the mirror and the distance between the mirror and the image, which means magnification also is the ratio between the image distance, which is V, to the object distance, which is U. But here we have to put the negative sign. So this one for the mirror. If the result was negative, for example, we have object distance 3 centimeter in front of the mirror. So it's to the left side. That's our object. And the formed image also in front of the mirror, but at distance 12 centimeter. How can we find the magnification? We will depend on the ratio of this distance of the image to the ratio of the object distance. this both in front of the mirror, that means the magnification here equal minus 12 divided by minus 3. And the magnification here is minus 4 times. The negative sign here means the formed image is inverted, which means beneath the optical axis. If it was positive, that means it's erect, which means above the optical axis, so that's immediately a virtual image. So negative, the image is inverted, and that's a real one. So in magnification, if the sign is negative, that's a real inverted image formed beneath the optical axis. If it's positive, that's a virtual image, which means it's erect, formed above the optical axis. Let's have another example. So we have object 4 centimeter in size and place 25 centimeter from concave mirror. And that concave mirror has focal length equal 15 centimeter. So can we find the location of the image and the nature of that formed image? From those, the height of the object here is 4 centimeter, and it's positive because it's above the optical axis. And since this object to the left, which means in front of the mirror, that means our distance here, the distance of the object, or we can say u, will be negative. That's minus 25 centimeter. And since it's a concave mirror, our focal length also negative, and it's minus 15 centimeter. By using this formula, 1 over f equal 1 over the image distance plus 1 over the object distance, we can say 1 over the image distance equal 1 over the focal length, which is here minus 15, minus 1 over the object distance, and it's negative always since it's to the left. Then after calculation, you will find the image distance equal minus 37.5 centimeter. So the image formed at distance 37 centimeter. Negative sign immediately means that image formed to the left. So it's in front of the lens here, somewhere here. Since image is in front of the mirror, that immediately means our image is real. Real image always inverted, so it will be like that. At distance 37.5 centimeter. And since we have the image distance and the object distance, we can find the magnification. Not just that, we can also find the size of the formed image. We can say the height of the image to the height of the object equal the image distance to the object distance. Those two equal the magnification. So the height of the image to our object size here is 4 centimeter equal negative. The image distance, which is this one, minus 37.5 to the object distance, here it is, minus 25 centimeter. After calculation, we can find the height of the image equal minus 6 centimeter. And as you can see here again, it's negative because we said a real image, so it's inverted. The size of the image here is 6 centimeter, and the size of the object, as we said, 4 centimeter, which means we have enlarged image, which means we have enlarged image. that image, as we said, it's real, so immediately it's inverted. And that's the nature of the formed image. And this image 1.5 times bigger than the object. What if we brought a lens, a thin one, a convex lens for example, or even a concave lens, and we cover it from here with a metal, such as silver, to become a mirror, to form a lens mirror. This means when a light passes through this lens mirror, it will refract first, then reflect by this mirror here, like this, to refract for the second time. So here we have the convex lens, and we cover that lens from outside, which means convex lens plus concave mirror. So this system is positive one. For concave lens, the light also will refract for the first time by the lens, then it will reflect by the mirror here to refract by the lens for the second time. This is the inside part of the mirror, so we cover it from inside. That means we have concave lens plus a convex mirror. So this one a negative system. As you can see here, for both systems, the light will come via this first medium, mostly it's air, then it will refract by the second medium, which is the lens, and after reflection, it will refract for the second time back to the first medium, which is the air. So that's refraction number one. Here we have reflection, and that's refraction number two. So we need to count all of that to find the power of this system. All the refraction occurred by the first surface or the front surface. So we will depend on the surface that caused the refraction. If you remember when we said when we need to find the total power of the lens, we will add the front surface power to the second to the back surface power. So if we have a lens plus 5 here and plus 7 here, the total power will be 12 diopter. And remember, the total lens power different from equivalent when we have two different lenses with space between them. In the lens mirror, we will depend only on the front surface, and because we have two refraction, we need to use that front surface 2 times. So 2 multiplied by the power of the front surface. The mirror here also has a power, so we need to count it too. We will add it to the front surface power, that's the power of the mirror, to give us the total power of the system, which is the power of the lens mirror. But the power of the mirror is calculated here by using the index of the lens material, not air. And also the power of the lens, we need to depend on the refractive index of the lens because the light here refract inside the lens, refract after passing through this lens. Let's have an example so you can get it more. Let's say we have equiconvex lens, and equi, as we said, means both surfaces are equal, have the same curvature. So this equiconvex lens has power plus 10 diopter. And the refractive index of this lens equal 1.523. The back surface of this lens is coated, which means this lens will reflect the light. The radius of curvature for this lens equal 10.46 centimeter. What's the power of the lens mirror here? Since it's equiconvex lens, which means the front power equal the back power, that means the power of the front surface here equal plus 5 diopter. And here we have the refractive index and the radius of curvature for the lens. Since it's a convex lens and it's coated from this area, that means we will depend on the radius of curvature from the left side. And since it's to the left side, we need to put the negative sign. So the power of the mirror equal minus 2 multiplied by refractive index divided by R. If you wondered why we put the refractive index here, this area we didn't set the refractive index because mostly we put the mirror in the air. So this one equal 1 when we place the mirror in the air. If we put it in somewhere else, we need to count the refractive index of that medium. For example, water or glass. So in our example here, our medium is the glass. So minus 2 multiplied by 1.523. And since we need power, which means diopter, we need to convert those centimeter into meter. So the radius of curvature here equal minus 0.1046 meter. So the power of the mirror equal plus 29.12 diopter. It's plus because our mirror here is concave. So all the time, concave mirror works with the convex lens and quite the opposite. Convex mirror will work with the concave lens. Since we have the power of the mirror now and the power of the front surface, we can use our formula here. The power of the lens mirror equal 2 multiplied by the front surface, which is plus 5 diopter, plus the power of the mirror, which is plus 29.12 diopter. And the result is plus 39.12 diopter. That's the power of the system here. As you can see, the lens mirror has extra power more than the lens itself.